And we are like, hi everyone, my name is Sahil, and today we have a special guest amongst us, Ankita Ghosh. She was the first guest presenter on our channel, and today she's here to explain her paper ILSVRC. A little introduction about Ankita. She is final year computer science undergrad at Manipal. She's also the co-founder of Research Society Manipal, which is the sole reason that I got into research and I got the platform to pursue my research. Uh, Her research interests are in computer vision, deep learning, HCI, and computer graphics. Last year, she interned at Waterloo through MyTrax, and currently she's interning at IISc Bangalore, pursuing some very important problems in medical AI. Uh, Ankita, you can take over now.
Yeah, thank you, Sahil, for that introduction. Really humbled. Hi everyone. I'm Ankita Ghosh, and today I'll be presenting my paper on integrated score cam for axiomatic-based explanations. So I did this project in 2020, and it was led by Rakshit Naidu. He was a senior at Manipal at that point. Now he's currently in Carnegie Mellon. And the other co-authors from Manipal were Yash and Shamant, and we had Soumya Kundu from SRM, Institute of Science and Technology. So, about the paper, I'll just go about first introducing the topic of explainable AI, and then just explaining the work related to our the work related to Sahil. There's
Yeah,
I
the
think I
screen is
can't
blank,
see.
right?
Yeah.
Yeah, give me 1 second. There's some problem.
No. Okay, I'll just continue explaining like how I'll go about explaining the paper. Um, I'll just start with the introduction where I explain about what explainable AI is, why we need explainability and explainable models. Then I'll present the work, the related work, the work which has been done prior, and we'll probably spend most time in that part because without understanding the previous work, it's you won't be able to understand the what we have worked on in ISCAM. And after that, I'll go about explaining the different evaluation metrics that we applied to our method and the different
Ankita?
architectures that we have trained it on.
Ankita?
Yeah,
1 second. No? I'm just getting back my second screen. Yeah, you can see the video now?
yeah.
Okay,
So,
cool.
okay. So I think we can go to introduction now.
Right.
Yeah. Okay. Yeah, as we all know, convolution neural networks are now like deep learning ML in general is like are the go-to approaches for any problems you can say, and convolution neural networks specifically are what we go for when it comes to to the vision problems like classification, segmentation, or detection. Now, the thing with CNN models is that they are black box models, and we still don't really understand what is going inside in those models. And uh, in fields of medical and security, it's very this is a big issue because these are fields where you need to be sure of what you are putting out, where the results are coming from. You need some form of explainability or interpretability. So, because of these concerns, in the last few years, researchers have come up with explainable models. And explainable models not only help in like recognizing the failures of the models or the drawbacks, but they also help in localization tasks because they are essentially showing which information is important. So our approach was based on a class activation map-based method, and we apply a gradient-free approach. So when we talk about class activation maps, they are you can say the OG in the field of explainable AI. The first approach is taken, And and then later down the lane they got divided into two main categories, you can say, gradient based and not gradient based. And the problem with gradient based is that the behavior can be erratic, there can be saturation, bias can seep in. So which is why we try to take a gradient free approach. And in that gradient free approach we base our method on a model, on an algorithm called as Grad-CAM, and we integrate and we combine integrated grad in that Grad-CAM algorithm. So Sahil, you can scroll down. Yeah, so in this paper we basically do two things. That is, first is we develop the ISCAM model and we explain that. And second thing we do is we provide evaluations on this ISCAM, and we provide comparison with the previous CAM-based methods. So yeah, so I'll start with class activation maps first in the related work. So class activation map, in class activation map, the intuition basically comes from the fact that when you input, like when you feed a image into a convolutional neural network, as you keep going down the layers, the image size shrinks, but the number of channels increases. And this increase in number of channels is nothing but extraction of information or features. So as you're going down the model, the more feature maps that you have, all these feature maps are different features. And when we have a fully connected layer at the end, and classification is done, or anything is done, it is basically classifying based on these features, just like it happens in like a ML model. You can say you have a set of features, and like logistic regression is done. So similarly, there are a set of features and it finally classifies. So this is the intuition on which it is based. And yeah, so we have the yeah, so we have let's just take an example of a CNN in which the last convolution layer has 512 channels. And suppose it has 512 channels, and it has to perform prediction for 100 classes, suppose. So what we do is we have these 512 channels, and we apply a global average pooling layer. Okay, and then after this global average pooling layer, now we have a vector of 512, like a vector with 512 values, right? And then we input this into the softmax, and it gives a output, classifies it into 100 classes. So now what we do is basically we have the weights. Now we have 512 weights for every class, right? So class activation map is found for a particular class, usually the class that has been predicted, because that's the best way you can visualize the information, right? So we'll take the weights of the last layer for a particular class, and we multiply it with the feature maps in the layer prior to class activation maps. So you have these heat maps, and you do dot product with the weights, and then you do summation over it. And the reason ReLU is done is so that ReLU function is applied is so that yeah, basically you will just have positive values, negative values won't be there, because we want heat maps. And you take that, you had 512 channels, right? And now you have done the dot product, and you have summed it over. So now you have only one single feature map, and this feature map is the heat map, or the class activation map, you can say. And now if you apply this heat map like you lay it over an image, you can see the points which have we'll see examples of this later, where it is bright yellow or red, which means these pixels are important, and the parts which are blue or cooler tones basically are not that important. So that is how essentially class activation maps works, which was the first model, you can say. Yeah, so after this we'll go to Grad-CAM. And Grad-CAM, so the problem with class activation map CAM was that there was a architecture restriction where you need to have a global average pooling layer, otherwise the method won't work. So what Grad-CAM does is it generalizes this over a wider range of CNN architectures, essentially like any CNN architecture, you can say. So for that, what it does is it takes the it makes use of the gradient information, or you can say the backpropagation technique. So here again you can see the formula looks similar to what we have presented in CAM, but instead of the weights, here we have alpha KC, which is K corresponds to the K channel, C is for again the target class, and yes, I can
Yeah.
Yeah. Yeah, and so the alpha case is defined here, and what essentially is happening in Grad-CAM is you'll have imagine any architecture. Suppose you have CNN and then you have like 3 fully connected layers, or you have a CNN architecture till a certain point, like you have convolution layers, and you then have LSTM kind of an architecture, or you have a mix of both. So you can have anything in the front. It doesn't need to be linear, but you have a last layer of convolution, like you will have a last convolution layer, right? So you take that layer, and those are the activation maps that you'll consider, and you'll take the back propagation. Instead of taking it till the very end, you calculate the back propagation only till till those activation maps. So YC, which is shown here in the formula, is nothing but the score of the target class, which is the prediction. So it's essentially just back propagation, but only till the activation maps. And once you have this, you have a set of you can say feature maps, which have been only calculated back propagated till that point. Now you perform global average pooling on those set of feature maps, and you'll again have a vector of values. Now these vector of values are done dot product with the original set of feature maps that we had. I hope you guys followed that.
One second. So the backpropagation is whatever the architecture is after CNNs get over, you backpropagate the final loss till the final layer of a CNN, and then you what do you do with it? You have a you have average pool or max pool over it, and then
so once you have backpropagated it till that point, now you have a different set of feature maps, right?
Yeah.
So those feature maps, upon those feature maps, you apply a global average pooling.
Okay.
So now you again come back to the CAM, like what we did in CAM. Now you have a set of, values, which are basically weights, because you have applied global average pooling to those feature maps. So you now have a vector of weights, and you will multiply these weights with the original feature maps.
Okay. Original feature map of which layer? Of the last layer of CNN?
Of the last layer.
Okay.
Of the last layer. So you will multiply that with the original feature map of the last layer, and then you will do summation. So it will again give you one single heat map. So that single heat map is basically the heat map produced through Grad-CAM method. So that is how Grad-CAM generalizes what is done in the CAM paper. And that is essentially what is expressed through this formula shown here. And then after Grad-CAM was done, there have been variations of Grad-CAM, like Grad-CAM++ and smooth Grad-CAM++, which are basically optimizations. Grad-CAM++ does more optimization to like regularize the weights and so on. And smooth Grad-CAM++, what it does, it provides inputs, and it sends in a number of like n number of inputs, and these inputs have different variation of noises. And now whatever gradient is produced, it takes average of that. So now the gradient is not that erratic, because we are taking an average over different images, like the same image but with different noise. So these are essentially the optimizations. And but the problem, like I said earlier, with Grad-CAM and the approaches entailing Grad-CAM is that you need access to the gradients, which is not easy, and the behavior is also not always predictable. So we come to score-CAM, which does not rely on gradient. It only requires class activation maps and the output or the prediction score. So what happens in score-CAM is you have, so again it's the same thing, you have the CNN model, and you will have a last convolution layer, and those have a set of feature maps. Suppose they have, let's consider they have n number of feature maps. Now you take you upsample these feature maps so that they are the same size as the image, the input image, and now you use these n feature maps as masks for the input image. So you take the first class activation map, you put it over the image as a mask, and it basically use the important like it will use the important information only from that input image because you're using it as a mask. And then now you have this new input image, you pass this new input image through the network, and it will give a score, right? It will give a prediction. So you have a prediction. Now you have the second. Now you take the second
feature map.
Feature map. You repeat the process. You use it as a mask, and you have a new input image in which different features are highlighted, right? So again you pass it and you take the prediction for that particular class. So in this way, you'll do it n times for all the n feature maps, and the score that you have at the end for every feature map is basically what is alpha CK, which denotes the channel-wise increase of confidence. That's what that is what it is. And then again you multiply this, you perform dot product with the feature map which was taken as a mask and the predicted score. You apply dot product, and then you perform the summation over it, and again in the end you will have one feature map, which is the heat map or the score-CAM map. So that's how basically score-CAM gets rid of gradients. And now lastly we go back to integrated grad. Now what integrated grad the reason we call it axiomatic based approach is integrated grad first defines two attributes, you can say. So these two attributes are sensitivity and implementation invariance. Now implementation invariance says that if you have two different neural networks, suppose one has 5 layers and there is one with 10 layers, but the result product produced by them is the same, then essentially they are equivalent. Like whatever is happening inside them, the number of features they are producing or the way they are producing the features is equivalent, it's comparable. Okay. And this is important because when you read the paper of integrated grad in depth, they basically prove how their method is implementation invariant. So basically, like even if any sort of like input they are putting in the network, or they are changing the workings of the like inside the network, it will not matter. They basically establish that first.
Okay.
The second thing is sensitivity. So sensitivity basically says that suppose you take two different input images, okay, and they produce different predictions. So that means the features that are different in them should have different values, and that is very intuitive, right? Like if the predictions are different, then the features will be different. So using this definition, what integrated grad does is it defines a baseline, and the baseline here defined is x dash, okay, and you have the input image x. Now it defines a relationship from x to x dash, okay. and that is how you that is how you increment the value. And integral basically means you're incrementing at finer steps and performing summation, right? So that is what it claims, that you go from baseline till the input image using any function you want. So that's what the F stands for. Using the function you want, and you perform the integral, and that will give you a certain result. Now, to implement this in real life, what IntegratedGrad does is it takes a baseline as a black image with all values 0, and it takes an input image. Okay, and it defines a linear like a linear relationship between them. So the values start from 0, 0 like the baseline, and it also defines an interval. So it defines an interval, let's call it m. So m can be 10 or m can be 100. So the more the value of m is, the closer it is going towards an integration, right? Because infinite number of intervals, that's what integration is. So it defines this n interval, and it increases the input from the baseline till the final input image. So essentially you can imagine it like an intensity increase, something of that sort. It's basically an overlay of the two image, where you have certain weightage of the baseline and certain weightage of the actual input image, like it's shown here in the formula as well. Like what is inside blue indicates that in the blue ellipse. And then it is passed through the CNN, and that CNN model is essentially what is the function f over here. Okay, and you have the CNN model, you have some output, and yeah, you have some output, and alongside what is happening is you are taking the difference of the feature of the, like the current input image and the baseline. You are taking the difference between the two. So this becomes, you can say, the weight factor, the alpha factor, or that we have seen in the previously in the other methods, alpha factor, and then this becomes you multiply it with the whatever value we get from the function, and then you take the summation, which is essentially the integration. So that is how IntegratedGrad works. Like, this is the theoretical formula, and that is how they implement it in practical in a practical way using summation. So that's essentially all the context that is needed for understanding our approach, and our approach is based on IntegratedGrad and Score-CAM. So yeah, Sahil, you can go till I think you can go to the diagram directly, so it will be easier. Yeah, okay. So here we present our approach, our proposed method, and what is happening here, I think you can already intuitively understand what is happening here. So we have, you can say, the outer model or the outer algorithm is that of Score-CAM, and inside that we are introducing the IntegratedGrad. So here again you have the input image, you are passing it through a CNN architecture, and you have a set of feature maps, you are upsampling these feature maps. We will use these feature maps, and so in the first one you can see first feature map is taken, it is used as a mask, and you have a new input image. Now this new input image is basically the input image for an IntegratedGrad, and what we are doing is we are taking from baseline to the new input image, and we are passing it through a CNN model, and we are obtaining a value at the end, like we would do for an IntegratedGrad. Again, now coming back to the, like you can say, outer loop of the Score-CAM, you have the second activation map, and then you are using it as a mask. You get a new input image. Again, you are going from baseline till that new input image into the CNN, and you are getting a value. So we'll do this till the nth nth activation map or the feature map, and we'll have certain values. And now these scores that we have predicted in the end, again like we do in Score-CAM, we are multiplying the score predicted along with the the feature map, and we are summing over it. We are doing summation, and we'll get a final map, which will be the ISCAM, basically ISCAM feature map. You can say the heat map. So the reason we introduced this integration inside ScoreCam is to improve the way the prediction is done for the ScoreCam. So yeah, so normally in ScoreCam you have that mask, you are only calculating the value once, right? But here we are calculating, we have that mask, we have a different input, and we are going from baseline to that input image, and we are taking an average of that. So the score is at the end is basically more reliable. The weight at the end is more reliable. That's the whole proposition in this paper. So yeah, Sahil, you can scroll up once. No, up to just to here. Yeah. So yeah, the formulas here explain the same thing. Whatever I explained through the diagram. And yeah, so what here we do is we take n number of intervals. So in our case, we first experimented with different intervals. We took 10, 50, 100 and all, and it didn't really have much, it didn't have that much difference. Like the difference between ScoreCam and ISCAM is there, but varying the n did not make that much difference. So we kept it to a value of 10 later on. And we calculated the scores from 0 to 1, and then we take the average. Also, another thing that we do is we normalize the feature maps so that it is uniform, and all the features lie within a particular range, and it stays uniform. So we also do normalization. So yeah, that is what we have proposed as a novel method in this paper. And yeah, coming to the second part of the paper, we experiment with we do experimentations on this architecture, and we evaluate it with mainly three methods, you can say. First is visual comparison. Second is assessing the fairness, and for this we use various different sub techniques again. And third is called energy-based pointing game, which uses a bounding box and is based on object detection. And the way we experimented is we took 2000, we selected 2000 images randomly from the ImageNet validation dataset. So yeah, that is ImageNet large scale. I can't remember the exact full form, but yeah, it's basically the full name of the challenge that ImageNet initially proposed. And once we have evaluated, we do this evaluation on 5 other CAM methods as well: Grad-CAM, Grad-CAM++, Smooth Grad-CAM++, ScoreCam, and Smooth ScoreCam. Smooth ScoreCam, again using the same technique that I explained for Smooth Grad-CAM++. And again, the images are resized to a fixed value, and we perform normalization and everything on same to essentially maintain maintain fair results, and avoid any erraticness. And again, for the baseline is set to 0, as it is also done in the original paper. So to start with the visual comparison, yeah, so you can see here, this is basically, these are the heat maps produced by each algorithm, and a visual comparison on that. And you can see how in ISCAM, the features are like, the yellow part is more concise, and it points to the exact features of like the dog or the capuchin or the whippet and so on. So visually, ISCAM provides better results, and but yeah, visual analysis is not enough, so we go ahead and do like mathematics and metrics based analysis. So in this, we introduce three metrics, which are average drop, increase in confidence, and win percentage. And we do this on pre-trained. We do this on pre-trained VGG16 model. That's what we use. Apart from this, we also use ResNet and SqueezeNet for some of the uh, evaluations and metrics. And I'll come back to these definitions later. But first, we'll go to area under the curve scores. So, Sahil, you can scroll down.
Yep, the table, right?
Yeah, no, to the graph.
Okay.
Yeah. So, first I'll just explain what are like insertion and deletion curves and all. So, what the intuition here is that um, if the CAM method is correctly, if producing the heat map correctly, then when we are extracting, you can say the classification or the predictions will depend on the most important features, right? Like the most important pixels, which it has denoted in, like, you can say yellow and so on. So what we do in insertion is we start with a baseline, like a black picture, and we insert the most important 224 pixels according to that particular method. Like whatever Grad-CAM says are the most important, whatever ScoreCAM says, and so on, in that way. And we calculate the prediction on that. Okay, now we introduce next important 224 set of pixels, and we again calculate the prediction. And we keep doing this until we have introduced all the pixels, and we keep calculating the prediction at each step. So in insertion, what ideally should happen is the moment you are introducing the important features, it should be able to calculate it should be able to make the prediction, right? Because imagine it is predicting as a dog. So the background shouldn't matter in that case. It should predict it as a dog based on the dog's features itself. So there should be a steep increase in curve, and the area under the curve should be more in case of insertion. In deletion, it should be exact opposite. The moment you take out the important features, so what we are doing in deletion is we are starting with the input image, and we are taking out the most important 224 pixels and calculating the prediction. Again, we are taking out the 224 next important 224 pixels, and you are calculating the prediction. So in deletion, there should be a sharp decrease in the prediction, and the area under the curve should be lesser. So here you can see the graph, and in the graph, like you can see, ISCAM performs better, or at least at par, and better than most of the models here. So that's kind of the intuition behind insertion and deletion curves. And you can see here that ISCAM is in brown, and it performs better or at par with the other CAM based approaches. Okay, so coming down to the other three metrics that I had mentioned previously. So coming to average drop basically calculates the difference between the positive difference between the predictions made by the input image and the prediction made by the saliency map. Saliency map is basically when you overlay the heat map on the top of the image. So it calculates the positive difference between that. So in average drop, when you have a saliency map, ideally your results should improve, right? Because you are already highlighting the features that are important. So in case of average drop, the lesser the value, the better the model performs. The algorithm is performing, basically. Coming to increase in confidence. In increase in confidence, again, we do the same thing. We are calculating finding the prediction by passing the input image and the saliency map. And if the if the prediction for that particular class by the saliency map is more than by the input image, then we consider a value, but then we assign value 1, or if it is lesser, then we take it as 0, and then we take average over all the n values or the n images that we are performing it over. And yeah, in case of increase in confidence, the more the value, the better it is performing. Yeah, now coming to win percentage. Win percentage basically takes the ratio of the decrease in model's confidence, and it takes the ratio of the explanation map produced by ISCAM and explanation map produced by another algorithm. So this we compare SSCAM, ISCAM with two other methods, SSCAM and ScoreCAM. And with SSCAM we get a value of 59.25. With ScoreCAM we get a value of 52.35. And yeah, it basically indicates that ISCAM is performing better than these two models with respect to this metric. So yeah, Sahil, if we scroll down, then
what about table 1?
Oh, table, yeah, sorry. Yeah, so table 1 was related to the insertion and deletion value. So here you can see the insertion technique, like I was saying. So ISCAM performs, at par with ScoreCAM, you can say. And like whatever we is depicted in the graph, this is basically shown through the values. So yeah, this sorry, I skipped it. And yeah, now going to the next table. So here we have the average drop and the average increase. And this is performed on 3 different CNN architectures: VGG16, ResNet, and SqueezeNet. And here you can see in VGG16, ISCAM performs better than the other two. And even in the other two, it is quite close to the other methods. So yeah, so going to the last evaluation method that we have, localization evaluation. This is based on object detection and bounding boxes. So what is done here is that the input image is binarized, and if we have the bounding box values, so whatever is inside the bounding box in the input image is marked as 1, and whatever region is outside the bounding box is marked as 0. And these are then element-wise multiplied with the saliency map, and then we take the proportion of the saliency map values which are within the bounding box upon all the the saliency map, all the saliency map values, like all the pixels, you can say. So the intuition behind this, I think, is quite obvious if you think of it, because bounding boxes are essentially they are detection problems, and what CAMs are providing is also localization in a way. They are telling which are the most important features based on which the CNN model is making its prediction. So ideally, these important features should lie within the bounding box. So that is essentially what we try to test through the energy-based pointing game method here. And again, this also be calculated over the three different architectures which I mentioned previously. And I think the table. So here again we have the table, and you can see that again in VGG16, ISCAM performs better than the others, and even in when we come to ResNet 18 and SqueezeNet, it is quite close to like the results produced by ScoreCAM. So yeah, those are essentially the evaluation techniques that we applied, and yeah, like I had previously mentioned, the value of n did not matter, which is required for integrated grad, did not matter that much. And And yeah, this work can be used and developed further, especially in the medical domain. Uh, we can like deploy it for real world scenarios. So yeah, and to end it, at that point of time, Mr. Wang from CMU was like really helped us with this. He's the author of Score-CAM, and also thanks to Research Society, because this collaboration happened because of that initiative. So yeah, and that's the paper. So thank you.
That was an amazing presentation, Ankita.
Thank you.
If you have any questions in the chat, you can ask them. Okay, so I had a couple. One primarily was what was the reason that VG16 was giving like excellent results in all the experiments that you had? Like, is there an intuition behind the model size or something like that?
Yeah, I think I mean, essentially, the different architectures are the reason for the different architectures is the hope that they'll extract features in a more better way, right? Like the way, like the reason for all the efficiency and everything is so that the CNN models extract features in a better manner. So yeah, I think the way the features are extracted by the VGG16 model, like ISCAM, I think tends to interpret it in the best way.
Okay.
So that's what I can think of.
Okay, makes sense. And another question I had was when you're plotting this graph, right? So is like the image size fixed because it will depend a lot about.
Yeah. So we took that image size only, which we defined earlier. The I think 224 into 224.
Okay, so the
It's the
image
size
net
that.
one.
Yeah. Like we kept the image size like fixed throughout. It was 224 into 224, and yeah, and so yeah, like that's why we extract 224 pixels, so it's divisible and it
Oh,
fits all.
but it will have like three channels. So is it like pixel across all the three channels or?
No, we converted into yeah, we take only single channel
Okay.
for this. Yeah.
Wait. Okay, so amongst all, like basically flatten the entire image and the best 224 pixels are passed through it.
Yeah.
Okay.
Yeah.
Yeah, makes sense. And I think another question I had here was, uh, I was just guessing, but the reason we are getting yellow heat maps is probably because the baseline is black and it's moving towards white. So is that the reason why most prominent regions are yellowish because it's closer to white for some reason? Or
I think this is based on the, if I'm not wrong, this is based on basically the Matplotlib way of the way it produces the map. So in Matplotlib, what happens is if you have like lower values, it starts from purple, right?
Mhm.
And then it goes to blue, and then it goes to green, and in the end you have yellow.
Okay.
So I think that's how, like, using that visualization. So these are basically, the heat map are values, right? The yellow part are basically higher values,
Mhm.
and the blue part are lower values. So we are just visualizing that using colors, you can say.
Okay. Uh,
Yeah.
Anything else? Yeah. So how was the process of this project in general? If like, how did you begin with? What was like the inspiration when you started, and what were like key moments when you were working on this project?
Okay, so yeah, we have Rakshit here, and definitely the main credit goes to Rakshit, because he pitched this in, and he was like, who all are interested in working on this. And I have been working in the field of computer vision, and but I had never worked in explainable AI before. So this was a new topic. I had worked on like medical problem statements, but not so. Again, when I read a bit more about explainable AI, I realized that you can really use this in the medical domain. So you can connect these two topics, and yeah, and it looked like and then I started reading up on CAMs and Grad-CAM, and more than anything, I think it looked quite interesting. And at first, even looked challenging. So yeah, I really had fun working on this. And yeah, Rakshit only kind of helped us with what to do. He kind of divided the workload between us, and yeah, we even wrote the paper together. And this was my first paper writing experience as well. So even in that, again, Rakshit helped a lot. And yeah, so it was fun.
That's very sweet. Um, all right, I think that's all. We we don't have any more questions. So thanks a lot, Ankita, for taking some time out for this. Really glad to have you back. Uh, Hoping that you will come again for another paper explanation very soon.
Sure, sure.
Thank you everyone for joining. With that note, I'll end the stream.